Okay, so good evening everyone and welcome to the 10th session of this course, Dynamical System and Control. So today we will be mainly looking at the discrete dynamical control system, and then we'll talk about Lyapunov stability for autonomous and non-autonomous systems. Okay. Okay, so let's begin with this discrete system. So now instead of having, so earlier what we had is, so we had something like y prime equals ay plus bu, right, where y was in Rn, okay, y of t. So this whole thing was defined for in some interval 0 comma capital T, right? So this was the equation, and this yt was in Rn, and this a b were the corresponding matrix, u was in Rm, right? So we were dealing with this kind of system. So here continuous in the sense that this in domain of T is a continuous domain, like it's not, but over here we have points, right? So over here we have n plus 1 points, correct? So what now, instead of dealing with this 0 comma t, or let's say more general t naught comma t, so this was my earlier setup, right? So this was the earlier setup that we had to deal in this t naught comma t domain. Now instead what we'll do is basically we'll deal with discrete points. So maybe this one, let's say this is k naught, this one is k naught plus 1, okay, this naught. So this gap are some uniform gap is there, okay, need not be uniform in this case, okay, but okay, we don't need to be in, the gap need not be uniform as of now, okay. So these like k naught plus n. So now we'll have to solve this on these, just these points and not on the whole interval, right? So over here this is the setup that we consider these points, which is defined in this way. This is k naught plus 1, k naught plus n. So this is basically the interval, this intersection with natural number, okay. So this k naught is a natural number, and we are increasing 1 by, we are adding just 1 every time, okay. So in this case the gap is uniform, okay. So this k naught, so every time the gap is of 1 unit, okay. So here you have 1 gap. So if k naught is 3, this is 4, 5, 6, like that, okay. Okay, so this is the setup. So this will be the control system, so that y at k plus 1. So it's kind of, you are defining it inductively, that you know the information. So suppose you know the information at this point of yk and uk, so of y and u over here, then you can, from here you can deduce what is the value here, and again from here you can deduce what is the value here, okay. So this is the equation that you know at k naught, this is y naught, okay, and suppose u at k naught is also known to you, then you can calculate. So you have to find u of k naught, okay. So this is the control which you have to determine, okay. So as of now you just assume that as of now you just forget about this term maybe, okay. So this, suppose you have this y naught, so putting it here you will get y at 1, k naught plus 1. Again using this equation you can get y k naught plus 2, by putting it here you will get y k naught plus 2, right, in this fashion. Now as far as controllability is concerned, so this is the setup, okay. But for controllability, notion of controllability, we have this additional term. So this uk is the control, okay, which you have to determine. And what controllability will, the notion of controllability, I'll just explain in a few minutes. So as of now this is the setup, okay, and this is how you can compute each of the terms. So this is just the inductively what I have written here, okay. So suppose you know y at k naught, then you can get y at k plus 1, right. So y at k naught plus 1 can be written as a y k naught plus b u k naught. So as of now you can assume what is u at k naught is known to you, okay, and then you can derive y k naught plus 2, which is a of y k naught plus 1 plus bu k naught plus 1. Now again you can substitute this y of k naught plus 1 from here, right, over here. So you can substitute this whole value in this over here. So if you do it again 1 by 1, then ultimately for any m, okay, so m is between this 1 to capital N, Okay, so then you can write the expression of y k naught plus m in this fashion. Okay, you can just calculate inductively. Okay, so you got this expression. So this is the kind of solution what you are getting. So knowing information at the previous point, you are getting information for the next point. So you can, so over here you define this state transition matrix as this one, which is a raised to the power k minus k naught. So maybe I should compare here a bit from the continuous one. So I'll just do that. Maybe here I'll compare. So you remember this, in continuous setup we had this kind of thing, that phi of t comma t naught was e of a t minus t naught. This was the state transition matrix. In the continuous setup we had the exponential exponential matrix, right? So over here this state transition matrix is defined in this fashion. It's just the power of a, where here we had the series of a, but over here we had just the powers of k. Okay, so this is the transition matrix, and these are the few properties that you can simply check. So it's not that difficult. You can clearly see phi of k plus 1 if we do. So phi of k plus 1 if I do, so what is this? This is a of k plus 1 minus k naught. So you can take a and you can write it in this fashion, k minus k naught, and this is phi of k k naught. Okay, so a times phi k k naught. Phi k k is identity, right? By k minus k will become 0, so we'll get identity. Phi k naught comma k, this is k naught minus k, so that can be written as inverse of this. So that means basically phi of k naught comma k, if you write, you will get a of minus of k minus k naught, right? And this can be written as a of k minus k naught inverse. Okay, so if you know that a is invertible, so this is, in other words, you can write this a inverse of k minus k naught, right? These are the two ways you can write. So this is nothing but this phi of k minus k naught is a of k minus k naught is phi k comma k naught. So this phi k naught comma k is inverse of phi k comma k naught. Okay, and this is another relation, that phi of k comma k naught is equal to phi k comma k1 into phi k1 comma k naught. So k1 is the intermediate point of k comma k naught. So if you have, this is k naught, this is k. So if you want to determine phi k comma k naught, you can choose any k1 point in between. Then you can write this as phi k naught comma k1 and then phi k1 comma k naught. Okay, so all these properties, if you see, it was satisfied by this exponential matrix, right? So if these, you can check maybe. So these are the trivial checking. Okay, so, or maybe I should do it here. So if you check for this one, you know that phi of, I am talking about this one. Okay, so phi of, you know that t naught comma t or t comma t, if you do, you will get e of a t minus t, right, which is the identity matrix, right? Again, if you do this phi of t comma, or let's say t1 comma t2, so this is e of a t1 minus t2. Again using the same argument what I just used here, you can write this, I mean just take the minus sign outside, so you can take it inverse, so e of a t2 minus t1 and then inverse, right? So this is phi of t2 comma t1 inverse. And again the third property is also it's easy because you know this a. So if you want to check the third property, that is also easy. So phi t comma let's say t1 comma t2, if you do, write it as a t1 minus t2, and now you can add t3 and subtract t3. So you can write this as e of a t1 minus t3 e of a e of a t1 minus t3 into e of a t3 minus t2, right? So these are the properties for this continuous state transition matrix. Okay, so this was, So analogous to this, all these properties you can see is for this transition matrix. Okay, and now you can rewrite. So we had solution of this form, right? So we had the expression of solution for each modes given in this form, right? Now you can rewrite this. So assuming k equal to k naught plus m, okay, this change of variable if you do, you can write y of k in this fashion, where k is again, this k belongs to this set P, right? This set. Okay. Okay, so this expression you get. Now you can write this as a sum in the format of sum using this state transition matrix as this one, phi k comma k naught y naught, which is this term, and the rest of things you can write it as phi k comma I plus 1 into b u I. Okay, where I is varying from k naught to k minus 1. So I have just summed it up, all these terms together to get this. Okay, and if you want to write it further using this property, which one, this d property, okay, you can again simplify this one as phi of k comma k naught into phi of k naught comma I plus 1, right? You can write this. Now you can take phi k comma k naught outside, and then you'll get, so you remember the how the solution was given in the continuous setup. So y of t was given as e of a t minus t naught y naught plus 0 to t, or sorry, t naught to t, e of a t minus s, and then you had b u s ds, right? This was the solution. So this state transition matrix we had here, the same kind of thing we can see here, right? Instead of integration we have summation, okay, and the same thing remains. It's similar, right? So this u of I is basically in each of the sub interval it is taking constant value. Okay, so maybe phi. So what I want to say is, if this is your t naught, this is a capital T. Now suppose analogous to this you had this discrete point. Okay, so in this region, suppose this kind of function. So this is, let's say, f1, f2, f3, f4, f5. Now if I want to integrate this function, okay, so this is a function, so I am calling this value as f1. So this is my whole f, the graph of function f, which is discontinuous function. Now if I want to integrate this f over t naught to t, okay, so see, I mean, let's not confuse with this. So maybe I should write alpha is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. So these are on this axis. So this is the y axis and this is the x axis, or t axis maybe. Okay, and this, let's say, y. Okay, so what it says, this function f is given in this way. Now if you integrate this function, what you get is, in this region, so it said, let's say this is t naught, t1, t2, t3, t4, and this, let's say, t5, which is capital T, and this is, okay, this is t naught. Okay, so if you integrate this function, in this region you are getting alpha 1 times t1 minus t naught plus alpha 2 t2 minus t1, and so on, right? So this is what we are doing here in some sense. So this b of ui, okay, this and this are constant in this interval. So in this interval we are assuming that the function, so suppose over here the function, so now okay, so this is one way. Now what I should say, let me write that. So suppose this is what notation, so maybe okay, so this was, f was given to you earlier, this was the function. Now I am saying you don't have this function f, what you have is, this one. So suppose you know that at t naught the value is alpha naught, you know that at t1 the value is alpha 1. I mean, this is what we are doing, right? For each points we know the value over here, if you see, right, for each point. So now we are just concerned about these points, and this is, let's say, alpha 4, and this is, let's say, alpha 5, this is alpha 6, okay, this kind of thing. So what we are doing, from these values we are defining the function f, and how we are defining is, in this particular value we'll take this constant value, in this interval we'll take this constant. So this is hollow here, okay, this, and that's it, right? So now this function, what I'm defining now, if I integrate this function, this is basically the summation what I wrote here, right? So this is what we are doing, and this is how this summation integration. So integration in discrete setup is like summation, okay? So that's why you can see this summation symbol over here, okay? So instead of having this bus, and instead of having this e at t minus s, where t was varying from t0 to t, I am making this constants. So instead of t, I just have this point k comma k minus, so I plus 1 and k. So I mean these are fixed, right, in each of the. So if you break this, so let's say what is the first term, this is 5k k0 plus 1, right, and then you have this b of u k0, right? So I'm just writing one terms. So over here you can see this is fixed. So in this t0 to t domain, this is fixed, or let's say t1 if you want to put t1 then. So like this you are just making it constant. So you know how this okay, I think this kind of thing, you know how it comes, right? So suppose you have this solution. So let's forget about the control part as of now, maybe. So you suppose you have this kind of expression, right? Now using this you can write y at t1 is e of a t1 minus t0 y0, right? So suppose this is the function, this is the matrix A tilde, okay, and this is y at t0. Again you can put here t2. So y at t2 if you write, you will get e of a t2 minus t0 times y0. Now this can be written as e of a t2 minus t1 d of a t1 minus t2, sorry, t1 minus t0, and then you have y0. Now this is your y1 yt1, right? So y at t2 is e of a t2 minus t1, and then this y at t1. Now suppose this gap is uniform. Suppose this is some what should say, let's say this is k0 or some alpha. So then this is again alpha. So this is your a tilde again, right? So over here what we can see, that y at tk plus 1 is equal to a tilde y at tk, right? This kind of thing is there, right? So what we are doing, we are just evaluating at one point, and then we saw this kind of expression. So this is how this yk plus 1 is defined. So this is discrete in the sense you are point evaluating the solution, you are discretizing the solution, okay, not the equation. Okay, so maybe I should just, okay, so this is what I was saying, that over here we are just fixing this us at u at k0, like just at the initial value, the k0 point. So in this k0 to k0 plus 1, I am taking the value of u as this one, what was the value at k0, okay. I hope it is clear. If not, you can ask, okay. Okay, now this is one easy example, that you have yk plus 1 given by this one, a of yk. I mean the same thing, the same scenario. Here b is 0, the B matrix, okay. So over here you have to show that this phi of, so this is the state transition matrix phi. So phi of k0 plus 8 comma k0 plus 3 is equal to a cube into phi of k plus 2 comma k. So this is small k. I mean this is quite easy, just you know what is the expression, right? So phi, you know what is the expression of phi. So phi of k comma k0, you know that it is given by phi of a of k minus k0. This is the definition. Now you can plug it here. So phi of k naught plus 8 comma k naught plus 3, if you do, you will get a of k naught plus 8 minus k naught plus 3, and this is nothing but a raised to the power 5, right? If you evaluate this, you will get a raised to the power k plus 2 minus k, which is a square. So now this you can write it as a cube times a square, and you know that a square you can write it in this is equal to 5 of k plus 2 comma k. Okay, so this follows just from the expression of this 5. Okay, so you don't need to bother about what is k naught, what is k. Okay, okay, now let us try to calculate the solution explicitly, what I just mentioned over here, right? So the way we are calculating y inductively, so let us try to calculate for this particular example. Okay, so let us see what the equation turns out to be. So over here, this y of k is nothing but y1 of k and y2 of k. So we have two components. So over here you can see that y1 of k plus 1 is given by 3 of y1 of k, and y2 of k plus 1 is given by minus y1 of k plus y2 of k, right? And the initial, so this is, let's say this is your initial, that at 0 level you have this. Okay, so this k is from k equal to 0, 1, 2 and so on. Okay, so this is the system. So we have to find the value of, the explicit way to write the solution. Okay, so let us, so this, you know, there is no coupling in the first component, so let us try to evaluate that first. Okay, so y1 of k plus 1 is given to be 3 times y1 of k, and similarly I can calculate y1 of k plus 2, this is 3 of y1 of k plus 1, and this is nothing but 3 into 3 of y1 of k, right? So in this way I can say that y1 of k plus n for any n which is greater than equal to 1, I can write this is 3 raised to the power n times y1 of k, right? So in particular, let us put k to be 0, because I know the value of y1 at 0, right? So here k naught is 0, right? So this is your k naught. Okay, so I can say put k equal to 0. So what I get is y1 of n is equal to 3 raised to the power n and y1 of 0. Now what was y1 of 0? y1 of 0 was alpha 1. So this is 3 raised to the power n times alpha 1. Okay. If there is some lag, I think. Okay. So this is your expression of y1, where n is belonging to the natural number. Okay. Okay, so now let us look at y2. So y2 at k plus 1 is given by minus y1 at k plus y2 at k. Okay, now y1 at k you already know, that you expression of y1, right? So let's not worry about that. So now let us try to calculate what is y2 at k plus 2. Okay, so y2 at k plus 2, if you calculate, so this is nothing but minus y1 at k plus 1 plus y2 at k plus 1, correct? Now if you substitute the value of y1 at k, sorry, this is y2, am I doing something wrong? Okay, no, this is fine. So now I have to put this y2 at k plus 1. What is the value of y2 at k plus 1, right? So y2 at k plus 2 can be given as y2 at k plus 1 is minus y1. So let me write this. You have minus y1 k, and then you have plus y2 at k, correct? So in the same way, if you proceed, so you get that y2 so y2 at k plus n, okay, for any natural number n can be given as, so you see this y2 at k, if you note it, this expression, you see the y2 at k is there, okay, here also y2 at k is there, okay, the rest of the terms are of y1, okay, and these are starting from, so if you see here, so when it was k plus 1, this was k, when it is k plus 2, it is k plus 1, okay, and each are with the negative sign. So I can write this y2 at k plus n 1 n as y2 at k, this is something which is fixed every time, and the rest I can write it as, you start with minus y1 k plus n minus 1, right? So 1 less than this one, so 1 you have to reduce, and then just sum it up, you decrease it again by 1 and go till minus y1 at k. This is the form, correct? So if you put k equal to 0 again, what you get is y2 at n is given by y2 at 0, which you already know, and the rest are minus y1 n minus 1 minus y2 n minus 2 until you go to minus y2 at 0, right? This is from this expression, correct? So so you know what these values are. So y2 at n, you can, in more general, you can write it as, you can write in a short form, which is summation y1 at I, where I is varying from 0 to n minus 1. So this is the expression of y2, where y1, so y2 at 0 is alpha 2, right? And where y1 of I is given by 3 raised to the power I, what was it? So this one, times alpha 1, right? So this is the expression of y2. So this is how you can solve iteratively. This was a simpler one, where you can just do this kind of analysis to get this just computation a bit of, okay. Now let us talk about this non-autonomous system. So far this matrix A and B were constant, okay, so those were constant matrix. Now these A and B are also depending on the point value, okay. So if you have this k plus 1, so to get the expression of k plus 1, you need to know the value, the matrix A at k, y at k, b at k, and u at k, to get y at k plus 1, okay. So this is the system. Now again, what I just said, using the same kind of argument, like you have to solve it inductively, you will get this kind of expression. So y at k naught plus m can be given as a at k naught plus m, a at k naught plus m minus 1, dot 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 a at k naught times y naught, and then you will have similar kind of thing, right, times b k naught u k naught, and so on. So now this b of k naught will increase, so k naught plus 1 and so on. So ultimately it will end at k naught plus m minus 1, u k naught plus m minus 1, okay. So this is how you can write the expression of y of k naught plus m. Again, this you just replace k naught plus m by k, okay. So here I have done, okay. So before that, let us introduce what is the state transition matrix. So state transition matrix over here, so in the earlier case, phi of k1 comma k2 was a of k1 minus k2, right? And over here we don't need to worry about the powers, whether k1 is greater or k2 is greater, because a inverse existed, okay. But over here we are defining this phi of k1 comma k2 for k1 greater than k2 as of now. Okay, so phi of k1 comma k2, you can write it in, we are defining in this fashion. So you evaluate a at k1 minus 1 and then you multiply with the next a evaluated at k1 minus 2 dot 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 multiply with a at k2. So this is k1, this is k2. You evaluate matrix A at k2 minus 1, sorry, k1 is bigger, right? So k1 will be here, k2 will be here. So evaluate k1 minus 1, k1 minus 2, evaluate at k minus 3 till you reach at k2, and now you multiply all those matrices. So this is how you define this state transition matrix in this case. So again, the last solution, this all these things, okay, except d naught u naught. So it can be written as phi of k naught plus m because it's starting at k. Okay, I think there's some mistake. Is it? Yeah, there is some mistake. So here maybe it should be 1. Either here or here. Just a second. So if I evaluate k naught plus m equal to 1, yeah, I should get here, I mean this term should not be there. Okay, correct. Okay, so it will start with 1 less, and then you can write this as phi of k naught plus m k naught times y naught, and then this is fine. Okay, in the same manner you can write all these entries in this way, in form of a state transition matrix, and you can continue, okay, just using the expression over here. Now that can be rewritten, assuming this k naught plus m as k, you can write this yk in this fashion, which is a simpler form. Now over here, you recall here, using this property, the d property, I was able to write this phi k comma I plus 1 as phi k comma k naught and phi k naught I plus 1. Okay, over here, okay, so again here you can check few properties of this matrix phi. Okay, so let me write it here. So you can check for this phi matrix, you can see that this phi of, if you do k plus 1 and then k naught, okay, you can write this as, or maybe I should say here you can assume k is greater than k naught plus 1. So over here I am saying k is greater than k naught plus 1. Okay, because I have defined phi k1 comma k2 for k1 greater than k2 so far. So I can write this phi k comma k naught plus 1. If you evaluate, you just put it here. Okay, so what you get is a at k minus 1 dot 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 till a k naught plus 1. Correct? I have just written the definition over here. Okay, now what you can do, you can write it as a of k minus 1. Okay, the same thing whatever it is till here. Now I can write a at k naught and a at k naught inverse, right, just multiplying by the matrix A and its inverse. So over here the matrix A at each point k is invertible, so I can do so. Now this I can write, so these all things together I can write it as phi of k comma k naught multiplied with a k naught inverse. Okay, so this is one of the property, that phi of k comma k naught plus 1 can be written as phi k comma k naught and a k naught inverse. If you see, if you compare with, if you compare with what I said earlier for the earlier case, that phi of k comma k naught plus 1, if I try to use the earlier formulation, I can write this as phi k comma k naught into phi k naught comma k naught plus 1, right? So this is for the previous one, the previous where phi of k was given by, sorry, phi of k comma k naught was given by a power k minus k naught. Okay, so motivated by this fact, let's say I am defining, so over here this, see, this k naught is less than k naught plus 1, so I don't have expression, I don't know what is this in this particular case, because I know phi of k1 k2 for k1 greater than k2, but over here this k1 is less than this quantity, so that is why, so here what we want to put is phi of k naught plus 1. Let's say that we want to define in this way, so we are defining in this way. Okay, so this is the definition or the notation what we use, and this is nothing but, if you see this quantity, so a of k naught, what is a of k naught? It is phi k naught plus 1 comma k naught, right? So a of k naught I can write it as phi k naught plus 1 comma k naught. This is just by the definition. Okay, and this is inverse of that, so this is inverse. So I am defining this phi k naught plus 1 as inverse of phi of k naught plus 1 comma k naught. Okay, so in general what I can say, so this is the sort of how we define. So you can define phi of k1 comma k2 equals, so here k1 I am assuming it is less than k2, so this is for k1 greater than k2, and for this one I am defining it as phi of k2 comma k1 inverse. Okay, so phi k1 k2 is defined for k1 greater than k2 in this fashion, and when you go for the opposite one, when k1 is less than k2, you can define it as inverse of this. Okay, okay, so this is how you can evaluate the state transition matrix if k1 is less than k2. Okay, okay, again you can use the change of variable to get this formulation. Now using this expression of phi, okay, you can write this. Okay, okay, what I just said, I think it's written here. Okay, so this is what I can think of. So this is what I just said, I guess, and this is again you can prove, it's elementary, and this is what I was telling you how to find the inverse. Okay, and so for k naught plus m, you can write this phi of k comma k naught plus m in this fashion. Okay, so you see this, the product kind of rule, what was true for the earlier case. Now over here, this fact, this quantity is defined as phi of k naught plus m k naught inverse. Okay, so then using this product form, okay, you can write the solution in this fashion. Okay. Again, this is analogous to what you see in the continuous case. The same. Over there, you just replace this k comma k naught as phi t comma t naught. Okay, where A is time dependent matrix. Right. Okay, so we have this expression. So now you have this problem that, okay, this is again the same thing what I just said. Okay, so you have to evaluate this phi k1 comma k2 for k2, so you can remove this equal to. So okay, for equal to, so over here I said k1 greater than k2. When k1 is equal to k2, you define it as identity. Okay, so over here you have to find what is phi k1 comma k2. So as I just said, phi k1, phi of k1 comma k2 is phi of k2 comma k1 inverse k2 is greater than k1, and this you know how this is defined. So this you decrease k1 by 1 and then you go till k2. this is a at k2 minus 1, and then a at k2 minus 2, and go on till a at k1. You take the inverse. Now when you take the inverse, everything will get reversed. So a k1 inverse, a k1 plus 1 inverse, and you go on till a k2 minus 1 inverse. Okay, so this is the expression of this. Okay, so here a is invertible, so I can do this inversion. Okay. Now let us talk about the controllability for this discrete system. So over here you say that this system, this one, is controllable if for any given two states y0, yf, okay, so this is the final state, this is the initial state, there exists a sequence of control, so okay, u0, u1, un minus 1, such that when you solve this equation, at 0 level it is y0, and at nth level this should be yf. So this is similar to what you have seen for the continuous setup, that there you need y at capital T should be yf, right, instead of yt. Okay, do you have any question here? Okay. Okay, so in the continuous setup we had this kind of equality that at capital time T it should be yf, but over here we are demanding that at last point, so it is k0, it is k0 plus 1, so this is k0 plus, okay, I think here there is a typo, so this is k0 plus n, so at k0 plus n I want it as yf. Okay, so this is not yn, this is yn k0 plus n. Okay, here k0 is 0, I don't know why, so it would be better if I write here k0 equal to 0. Okay. Okay, so this is the definition, and analogous to the continuous case. Over here also the controllability is equivalent to this rank condition, that the system is controllable if and only if the rank of this matrix is equal to n. Okay. Okay, now let us talk about the stability. So we already saw in the previous sessions that how to deal with the stability. So for linear system it was very easy. You just have all the kind of characterization using the eigenvalues, right? So whether the system is stable, unstable, or asymptotic stable, we could say just using the eigenvalues of the matrix, right? Now for the nonlinear system there are two approaches, and both of them have been discussed earlier. Okay, so so as of now we'll just talk about the autonomous case, where on the right hand side there is no t involved. Okay, so we are talking about autonomous. So how you can study this stability of this kind of system? Okay, so we'll see that, although I think these have been discussed, but we'll see today a few more things regarding the Lyapunov construction. Okay, so that would be, I think, new one. Okay, so anyway, let's begin. So suppose this yt is this f, so f is like this, you have n components, okay, and y is also has n components. Now you assume that's fi, and the partial derivatives of each of these components of f are continuous. Okay, so that you can guarantee the existence of solution by Picard's theorem. Okay, and you assume this f of 0 is 0. Now why we assume this? Because so that we can say that y equal to 0. So this tells you that y equal to 0 is an equilibrium solution. Okay. Okay, so now how do we study the stability of this? So we saw that either you can linearize this. Okay, so we had one more aspect, that you linearize this around this equilibrium solution. Okay, so when you linearize, you will get this kind of system. Now using stability of just this system, okay, using the information about the stability of equilibrium. So again, for this system, so here A is invertible, okay, and then you can see that Y is an equilibrium solution. Okay, so using the stability of equilibrium solution or trivial solution for this linear system, can we say something about the nonlinear system? Equivalently, using the eigenvalues of A, can we say something about stability for the main nonlinear system? Can we say that? And we saw that we can say, except one of the cases when the eigenvalues has real part equal to 0, in that situation we cannot conclude, right? If the eigenvalues were negative, then we said that the nonlinear system is asymptotic stable. If the eigenvalues had one positive real part, in that case we said that the nonlinear system is unstable. But when the eigenvalue contains one of the eigenvalues such that the real part is equal to 0, in that case we cannot conclude, right? And we already saw one example. I'll repeat that again. Okay, so maybe in upcoming slides. So in these cases we saw that except one of the case, so except the case when the real part of lambda is 0, where lambda is the eigenvalue of A, except this case we could conclude, but for these cases we could not. Okay, and over here obviously this G has to satisfy some condition, and which was like this, right? So limit, so first thing should be that G should be continuous and everything, and limit G of y upon norm of y, this should be 0, right? So this is the condition what G should satisfy. Okay, so this was one of the approach, that we linearize the system, and then we, using the eigenvalues of the linearized system, we tried to conclude about the nonlinear system. Okay, the other approach is using Lyapunov function. Okay, but the difficult task over here is that how to choose the Lyapunov function for general systems. That is the difficulty over here. Okay, so we'll see some of the method, but that does not guarantee that each time you will be successful in finding the Lyapunov function, but in many cases you can do so. Okay, so today we'll mainly talk about this part. Okay, and this is the example what I was talking just now, that there is some disadvantage of linearization. Suppose this is the cases. Suppose these are three different examples. Okay, in the first case the equilibrium solution is asymptotic stable. In the second case this is unstable, and in the third case this is stable. Okay, but if you see the linearized part, okay, so the linearized part is this one. Okay, in each of the cases if you linearize the system around y equal to 0, you will get the same matrix. Okay, and in this you see the eigenvalues would be plus minus iota for this matrix, so the real part is 0. So in each of the cases the linear system is stable, right? So in all the three cases the linear system is stable, but the corresponding nonlinear system shows different behavior. So as in the first case this is asymptotic stable, the second one is unstable, third one is stable, right? Do you remember how to prove that this kind of thing for these examples? So over here what was the the Lyapunov function? So in all the three cases actually you can try with this v of y1 y2 equals y1 square plus y2 square. This Lyapunov function will work for all three cases, right? Do you want the explanation or is it fine, or you will be able to do this? What do you think? Okay, this was already, anyway this was discussed earlier, this kind of thing. Okay, so what you just do, okay, anyway I'll be discussing about how to check this kind of thing. So using that theorem you can verify. Okay, so this is the theorem, that suppose that you have been, this omega is any open set which contains the origin. So over here we are talking about the equilibrium solution y equal to 0. Okay, so we are assuming that y equal to 0 is equilibrium solution for the system, concerned system. So that's why we need this origin to be in 0 in this omega. Okay. So now you have to find, if you are able to find a scalar function which is this v, so this omega is some open set containing the origin. Okay, so if you find v which satisfies these two properties, which is the first property is that vy should be strictly positive for all the points except 0, and at 0 it should be 0. So this is the first condition. The second condition is that if you differentiate this v with respect to time, okay, now see, this v is a function of y, but over here I am not talking about v of y, so I should have written here v of yt to be more precise. Okay, so you are differentiating this v of yt with respect to time, then that derivative should be less than equal to 0. If this is possible, if you can find such v, then in that case the equilibrium solution y equal to 0 is stable. Okay, so you have to find such function v. If you are able to do so, then you are done. Then you can say that y equal to 0 is a stable equilibrium solution. Okay, but when you want to talk about asymptotic stability, you want to add one more point, which is this should not be less than equal to 0, but it should be strictly less than 0. Okay, so this time derivative should be strictly less than 0 for omega minus 0, and at 0 it will be 0. Okay, so except the origin it should be strictly negative, the derivative. In that case you can say that the equilibrium solution is asymptotic stable. Okay, using these, okay, there is one more theorem about instability. So using these three theorems you can actually conclude about this. So over here you just find what is d dt of v y1t y2t in each of 3 cases. Okay, and this is nothing but this is grad v, okay, dot this f. So this is your f, right? This in each of the cases this is your f. So you do this dot product and you check when it is strictly negative and when it is less than equal to non-positive. Okay, so for the instability you have to have this kind of property. So the first is, okay, this is same as the last one. Okay, the second one is that this grad v times f should be positive. Okay, for omega minus 0 it should be positive, and at 0 it is 0. The third property is what it says that for any neighborhood, so if you have this 0, now you take any neighborhood of 0, okay, whatever neighborhood you choose, there should exist a point y0 where this function v is strictly positive. Okay, so here we are not saying that v should be strictly positive. See, earlier we said that v of y should be greater than 0 for y not equal to 0, but over here we have not said such things. Okay, so you have to find a function v which is equal to 0 at 0 and whose derivative with respect to time is positive. And the third point is that for whatever neighborhood you choose, okay, there should exist some point in any neighborhood where the function v is taking positive value. If this is the case, then in that case the equilibrium solution would be unstable. Okay, so in the last example is a good one to check all these properties. Okay, in all the 3 cases I think this Lyapunov function will work. Okay, now this theorem, okay, so what is a Lyapunov function? So Lyapunov function is like this. So suppose, so this Lyapunov function, we say a function v is Lyapunov if corresponding to that the equilibrium solution 0 is asymptotic stable. Okay, Okay, so you can see that these properties is actually the property that you need to have for asymptotic stability. Okay, so that's it. So this function is called Lyapunov if it satisfies these two properties, which is same as required for asymptotic stability. That's why sometimes asymptotic stability is also called Lyapunov stability. Okay, just because this is characterized by this kind of function. Okay, now there is a theorem which guarantees that Lyapunov function will exist. And what the theorem is, that suppose this y equal to 0, you know by some means that it is asymptotic stable. Okay, if it is asymptotic stable, then there will exist the Lyapunov function. Okay, so you know if there exists the Lyapunov function, you know that the origin is asymptotic stable, right? The equilibrium solution is asymptotic stable. Now this is somehow it's converse, that if you know that origin is asymptotic stable, then you can guarantee that there will exist a Lyapunov function, but you don't know how to construct that Lyapunov function. Okay, so construction, how to get that Lyapunov function, that you don't know, but you can still say that there will exist such. Okay, now let us talk about the construction of Lyapunov function. Okay, so this is one of the approach. So what you do basically, that you assume that the gradient, so you have to find what is v. Okay, so v of y1, y2, yn, this is your goal. Goal is to find this function v, which will guarantee the Lyapunov or asymptotic stability. Okay, so for what you do, for that you assume the gradient has this kind of form. Okay, so here this is not, these ai's are not constant, so these are functions of y. Okay, so these are functions of yns. Okay, so you assume that the gradient v has this form, which it has n components and each of them are defined in this fashion. Now the goal is to find what are these ai's, right? These are unknowns to you, this aij. Okay, for that what you do, you put this condition that the grad v times f should be negative. Okay, in any neighborhood of 0. Okay, so you have to remove the 0 origin, so in any deleted neighborhood of origin. So considering this fact in mind, you just try to find or guess what will be aij's. Now once you know what is aij, so suppose you know what is aij and you know that this is nothing but del v by del y1, del v by del y2, this is del v by del yn, right? So if you know all the expression, you can solve these PDs, right? Just by integrating or doing some manipulation, you can solve this n number of PD system to get what is your v. Okay, we'll discuss few examples, the basic example, not too complicated one, to see how it works. Okay, so let's start with this. So this is something what I have picked from the example that I stated earlier. So I picked this one. Okay, when it is, obviously we are talking about finding Lyapunov function for asymptotic stable case. Okay, so for these cases we are not saying that how to construct, we are talking about this case. So when I say Lyapunov function, I mean this one for this case. Okay, because that is guaranteed by that theorem, that if you know that origin is asymptotic stable, you know that Lyapunov function exists. Okay, so I have just picked this and I have already said that this v will work. Okay, this, so I have given you one Lyapunov function, but let us try to see how you can construct in this using this variational approach. Okay, so this is the example. So what you do, so you assume that the grad v, so over here we have this two components, so we'll have this 2 cross 2 matrix which is function of xi's, so a11, a12, a21, a22 times this y1 y2. So this grad v of y1 comma y2. Okay, so these aij's are function of y1 comma y2. Okay, or in other words you can write it as a11 y1 plus a12 y2 a21 y1 plus. Now what you want to make sure that if you multiply, do the dot product grad v of y times f of y, this should be negative. This is your goal in mind, right? So let us try to see what is this dot product. So grad vy dot f of y, if I do, so let us see what is f of y. So f of y is nothing but, from here I can say this is minus y2 minus y1 cube minus y1 y2 square, and here I have y1 minus y2 cube minus y2 y1 square. So this is your f. Okay, let me write it here. Okay, now if I do the dot product, what I get is so a11 y1 plus a12 y2 times minus y2 minus y1 cube minus y1 y2 square plus, so a21 y1 plus a22 y2 times y1 minus y2 cube minus y2 y1 square. Okay, so maybe I should do it here. Okay, now if you see from here, so if I multiply this a1 with each of the terms, what I get is, so minus I can take outside, minus a11. Okay, if I multiply, what I get is y1 y2, and then you have y1 4 plus y1 square y2 square, right? So you see these terms are fine. I mean this is fine because they are positive. So giving sign on a11 will give me sign of this quantity. I mean this is the problematic term, y1 y2 cross product, but okay, we'll see what we can do for that. Now let us look at for the a12. So again minus a12, if you do, you'll get y2 square. Okay, and then you have minus y1 cube y2, then you have minus y1 y2 cube. Okay, if you go for a21, so you can say minus a21, if you calculate, you will get y1 square. So here you will get minus y1 square, and then you have plus y1 y2 cube, and then you have minus y2 y1 cube, so plus y2 y1 cube. Okay, if you go for the third last term, so minus a22, it is y2 y1, and then you have minus y24, sorry, it will be plus, just a second, here it will be minus, right? And then here you will have plus y1 square y2 square. Okay, so let us see what are not problematic. So this is not problematic, this is not problematic, again this is problematic. Okay, so you see, okay, so maybe I should use different color for, again these are not problematic. Now the problematic terms are this and these terms, right, because of the odd power, correct? Now if you look at these two terms, Okay, then you can clearly see if I choose a11, okay, such that which is equal to a22. Okay, so if a11 is equal to a22, then this problematic term is gone, then y1 y2 terms are gone. Right, because of this minus sign over here and here plus sign. Now rest of them I don't care, I'll just put this 2 to be 0. Okay, so what I'll do, so maybe now choose a11 equal to a22, let's say to be 1. Okay, okay, why I need positive? So see over here, maybe let me write one more line. So let's choose for this first, this one, choose a21 equal to a22 equal to 0. Okay, the other term, then del v dot f, you can see that this is nothing but, copy this, then copy this. Okay, so now if I choose, if I ignore this y1 one term, so as of now choose a11 equal to a22, then what I get is minus a11 y14 plus y1 square y2 square minus a22 y24 plus y1 square y2 square. Now clearly these are positive quantities, like non-negative. So this is strictly less than 0 for if y1 not equal to y2 not equal to 0. Correct? So over here I am assuming a11 and a22 are equal and non-zero. Okay, then we know that this is strictly less than 0. Okay, so now we just need to, so this is true if, so for maybe for and if a11 is positive. Correct? So in particular choose a11 equal to a22 equal to 1, right? Then what will be the expression of grad v? Grad v will be a11 is 1, so 1 times y1 and then 0, and here I'll have y2, right? If I substitute it here. Okay, so now this is equal to, now you know that this grad v, maybe I should write here like this, and this is nothing but del v by del y1, and this is del v by del y2. Okay, then from here you can, if you integrate, so if you integrate this with respect to y1 and the here with respect to y2, you will get v as y1 square plus y2 square. Correct? So ultimately you will get v of y1 y2, maybe if you want to write half you can include, because when you integrate you will get y1 square by 2. So this will be your one of the v, right, if you integrate this. Okay, so this is the same Lyapunov functional what I told you earlier. So it's just 1 by 2 you multiply, that does not affect. Okay, and note, okay, so if you integrate here you will get a constant here as well, right? So if you integrate you will get a constant, but for Lyapunov function what you have to guarantee that v at 0 should be 0. So for that this c should not be appear, it should not appear, right? So this c I am removing just because v at 0 is 0. So this would imply v at 0 comma 0 is 0. Okay. Okay, so this is how this variational approach works. Okay, again we'll see this example. Okay, so over here we have 3 cross 3 system. So again what you do, you assume this grad v to be a11. So over here all are xi's, so x1 2 x2 a13 x3 a21 x1 plus a22 x2. Okay, so this is the grad functions. Okay, now what is your f over here? So f, let me write here, f of x is minus x2 minus x1 x2 square plus x3 square minus x1 cube x1 plus x3 cube minus x2 cube minus x1 x3 minus x3 x1 square minus x2 minus x3 5, right? So this is your f. Okay, again as before we'll calculate the dot product of this function, right? So grad v dot f, if I do, although it would be lengthy, but can we make it a bit short? Okay, so what, maybe let's try it, we'll see. So a11, if I do, I just multiply this by x1, so minus x2 x1 minus x1 square x2 square plus x1 x3 square minus x1 4. Okay, so as of now let's ignore these terms, okay, the off diagonal terms. Okay, the reason being that I want all these to be zeros. So let's see if we can do it with this. So I mean I'm just following the arguments as done before, that I made all the off diagonals to be 0. So that why I did that, because in that case I'll get this simpler version where when I'll talk about the partial derivative with respect to y1, I'll just get terms of y1. I don't get y2 y3 or anything else. Okay, so because of that diagonal form I'll just get y1, so I can simply integrate it. The same logic works here. If I get del v by del y2, if I get y2 on the right, then I can simply integrate with respect to y2 to get the expression of v. If I get some coupling, then there might be, I mean we'll have to see how to solve that. Okay, so for this example at first I'm removing all the off diagonal terms, and let's see if it works or not. Okay, so in the starting only I'm assuming all the off diagonal entries are 0. Okay, and let's see if that works or not. So this is the for a1, and then for a22 you just multiply by x2. Okay, in the second one, so you get x2 x1 plus x2 x3 whole cube minus x2 4, and if I do it with the third one, a33, multiply x3 here, so minus x1 x3 square minus x3 square x1 square minus x2 x3 cube and minus x3 6. Okay, so over here also let's first see what are the non-problematic term. So this is clearly not problematic at all. Again, this is not problematic because these are even powers. Here this is not problematic, here this is not problematic, this is fine. Okay, now let us see the problematic terms. Okay, so let us see what are the same terms which appears. So for this one, x1 x2, you see this cross product appears here, right? Okay, for the next term you can see this x1 x3 square and this x1 x3 square, right? What else do we have? Now here this x2 x3 cube appears here. Now see, all these have opposite signs. So if this is plus, this is minus. If this is plus, this is minus, right? So we have opposite terms all the time. Okay, so maybe in the next page I should write. So over here, if you see that if I choose, so maybe let me write in this fashion. So okay, so let me write not problematic terms all together. So a11 with minus a11 with x1 square x2 square minus x14, sorry, plus x14, and then minus a22 x24, and then minus a33 x36, correct? Okay, so these are good terms. Like if I choose aij's to be positive, then I'm done. Like this part will not create a problem. Now if I choose if I look at the other terms, so for x1 x2, so if I choose plus x1 x2, see it is minus a11 plus a22. For x1 x3 square, I have plus a11 and then minus a33, and for the other term which is plus x1 where is it, x2 x3 cube, if I do, I'll get a22 minus a33. Okay, so this is my grad v dot f. Okay, now the first condition for looking at these terms is that
one more,
yeah,
x1 square is also there.
have I missed something? Which one?
x1 square x3 square. Okay, it is not cancelled.
Oh, x1 square x2 square, this one,
x3 square last a33 x1 square x3 square.
oh okay, this one, right,
yeah.
sorry, x1 square x3 square, correct. So here I'll have x1 square x3 square and then plus x36, right? Okay, so now over here the first thing is that I need all these a11 a22 a33 to be positive. Okay, so aii is positive. This is the first thing I should make sure, because this I am calling that they are not problematic. That means these constant must be positive. The second thing is that these cross product terms should vanish. So I need this a11 plus, so minus, so this should be equal to a22 from here, and this says that a11 equals to a33, and this says that a22 equal to a33, and we see that all these are compatible, right? So all this says that a11 equal to a22 equals a33. Okay, so choose a11 equal to a22 equal to a33 to be 1, right? The simplest thing. Okay, then we are done. If I choose this, then obviously del v dot f is strictly less than 0 for okay at y, for y not equal to 0. Okay, and then we got the Lyapunov function. Then what is the Lyapunov function? So del v by del y1 is y1, del v by del y2 is y2, and del v by del y3 is y3. So if I solve this, I'll get v at y is y, so half y1 square, y2 square, and then y3 square, right? So this is the Lyapunov function, what I get. Okay, okay, now let us talk about the another construction. So I hope this is clear. I mean, this was quite easy. So the main thing was I removed the off diagonal term. Okay, because if off diagonal terms appear, so suppose if I get here plus y2, then it might create a bit complicacy, right? So it's better to first see if I remove the off diagonal term, then it works or not. If it works, then we are done, and we don't need to bother about that. Correct? Okay. So now let's talk about the another method or way to construct Lyapunov function. So here what you do, you at first you choose some non-negative function. So this is not negative, it is negative definite. It should be. So it is negative definite function. So what it means is basically, so phi at y should be less than 0 and phi at 0 should be 0. So this is for y not equal to 0. Okay, so this is what negative definite means. Okay, so choose any negative definite function phi, okay, around this domain containing origin, and now consider this differential equation. So now you want to solve this differential equation, okay, for v. So now this v is the thing that you want to calculate, right, the Lyapunov function. So define this system as d dt of v should be equal to phi, okay, and v at 0 should be 0. Okay, so it's like initial value problem. Okay, and then if you integrate it just from this t0 or 0 to t, capital T, then you will get this kind of thing, v at yt minus v at y0. So this y0 is y0. Okay, so v at y0 equal to t0 to t phi of yt dt, just if I integrate this. Now if I take the limit as t goes to infinity, okay, then what I get is, so okay, the first thing is that when you talk about Lyapunov function, you need C1s, right? Because you talk about the derivative d dt of v. Okay, so C1s is there for the v function. So this v is continuous. Okay, this v is continuous. Okay, now if you take the limit as t goes to infinity, then you know that since you are looking for a Lyapunov function, then your solution y should satisfy that y at t will go to 0 as t goes to infinity, right? This is what asymptotic stability means. So that's why this yt will converge to 0 as t goes to infinity. So this goes to 0 as t goes to infinity. Okay, and you know at v at 0 is 0. So this will be, now if I take limit in this identity, I'll get 0 minus v at y0, okay, minus t0 to infinity this. Correct? So now this 0 I am removing. So I get this. Okay, so here I think, so negative I have thrown it here. Okay, so this is the identity what I get. Now you see, since phi is negative definite, so minus phi is positive definite, and that's now we are integrating the positive definite function, then this v is also a positive definite. Okay, so you got v, expression of v for any y0. Now y0 was arbitrary, right? So you got the function v, what you wanted. Okay, so this would be a Lyapunov function, which is obviously this is positive definite, and you know that the derivative is going to be negative because negative definite because of this identity. So this v is the desired Lyapunov function. Okay. Okay. So let us now look at this example. So this is one dimensional. Okay, so x prime is x cube minus x. Okay, now this has been chosen from your assignment problem. So suppose this is your differential equation, and now suppose v is a Lyapunov function which satisfies this property. Okay, then you have to determine what will be v. Okay, so first thing, you can clearly see that this is not non-negative function, negative definite function. So it's actually similar to this kind of this identity, what this one, right? So you have that dv by dt is minus 3x square. So you have to determine what is v. Okay, so that's the basic goal. So we'll just follow this argument, what I have just said for this particular problem. Okay, so let's begin. So what you know is dv by dt is minus 3x square, correct? Now if I integrate, so I'll get v at xt minus v at x0. So is it okay, so v at x0 is equal to, so this would be from 0 to t minus 3x square t dt, right? So I have done nothing, I have just integrated this this thing. Okay, another thing what I can say here, okay, I should not write in directly this way. So actually so let us see what is dv by dt. Okay, so dv by dt, okay, this is nothing but dv by dx. Okay, so what I said earlier, that dv by dt, so because this is a function of xt, right? So you have to first differentiate with respect to x. So in n dimension we know this is grad v times x prime t, right, which is f. I mean, when we have this x prime equal to f kind of equation, right? So let's look what is d dt of v. So this is dv by dx, okay, times dx by dt. Okay, okay, so now, because then only I can integrate with respect to this t, then it will be easier. So dv by dx, okay, so dv by dx, let it be, we don't know the value, we have to find it. And then dx by dt, you know, dx by dt is equal to x cube minus x. This is x cube t minus xt. Okay, so this dv by dx is equal to 1 by x cube minus x times dv by dt, which is x cube minus x times, this is minus 3x square, right? So you got dv by dx equal to, so minus 3, so x I can take common from here, so I'll get minus 3x upon x square minus 1, right? So this is the differential equation. Now it's an easy, like you don't have to do all these things. So one method could be that what I just said, you can use that argument to calculate, I mean to get through this, or just directly this one. So I'm just removing this one. This would be easier, I guess. So you got this kind of differential equation, which is very easy to solve, right? You just integrate with respect to x. So integrating with respect to x, okay, you got v at x equals minus 3x on x. So let me take 3 outside, so minus 3x on x square minus 1 dx. I can clearly see you just have to take y equal to x square minus 1, then it will be derivative. So let's multiply 2 and 2, then you can simply integrate to get minus 3 by 2. This will be log of the, if you take y, so this is the substitution that you need to do, okay, then you get this. So log of x square minus 1, Now you notice one thing. So this obviously when x is not equal to 1, I am doing all this. So here I should have mentioned that x is not equal to 1. Okay. Here, so let me do it, write it in this way maybe. So dv by dx, so let me say this in this way maybe. So this is x times x square minus 1 is equal to this is dv by dx, and dv by dt is known to be minus 3x square. So you assume x is not 0. So if x is non-zero, you can cancel this term, then you will get dv by dt, x square minus 1 dv by dx equal minus 3x. So for x not equal to 0, and here for x not equal to 1, you can take this in the denominator to get this. Okay, so here this is for x not equal to 1 and x not equal to 0. Okay, so this function, the integration will be this when x is not equal to 1. Okay, then only you can integrate this to get this. Okay, and one more thing, that v at 0, you can clearly define it to be 0. Okay, so maybe I should write here, just a second. So over here, when we integrate this from this indefinite integral, I'll get this for x not equal to 0. Now you recall that the function v, what you wanted to define, should be some omega which contains origin, right? So it should be any open domain. So what I'll do, since I don't want this x to be 1, so I'll define it in the open interval. So this should not be equal to plus minus 1 in fact, so x should not be plus minus 1. Okay, so you define it v from minus 1 comma 1 such that v of x equals minus 3 by 2 log of x square minus 1, okay, when x is non-zero, and 0 when x is 0. So this is when x is not 0. Okay, so this will be the answer that you can check that this is continuous. Okay, and in fact this will be C1. So you have all those desired property what you are looking for this v. Okay, so this will be the function, the Lyapunov function. So you got what the v is. So it is a logarithmic function, okay, defined in this fashion. Okay, do you have any doubts?
Minus 3 by 2 or plus 3 by 2?
Was it
Log will be always positive.
Yeah,
V should be positive definitely.
yes, so the log, if you calculate this value, you see, I understood what is the doubt. So if you calculate this x square minus 1, okay, what is the domain? I mean, what will be the value it will take? So x is between minus 1 and 1, right? So it is negative.
Okay.
So then, sorry, I mean not negative, just a second. So x square is basically 1 less than 0. Yeah, it is negative. So log of 2. Okay, just a second, I did a mistake, I think. So when you, so integration of 1 by x dx is log of mod x, right? So here it should be mod. Okay, so this is the first thing. Now I think, okay. So what you basically do, you just, that would be a better way to write. So uh, you do 1 minus just a second. So if you do change of variable, so here you will get 2x, so you will get minus 3 by 2. Okay, I got it. So this is, if you take this mod, now this is nothing but, I can write this as 1 minus x square, right? This is 1 minus x square, because if you remove mod, because x is in minus 1 to 1. Now this 1 minus x square is less than 1. This quantity is less than 1. So this log will take negative value. Okay. So ultimately you will get positive value for v.
Okay.
Now I think this is fine, right? So I did a mistake over here, that while integrating you have to take mod, because integration of 1 by x is log of mod x. Okay. Yeah, but thanks for pointing it out. Okay, so this is the answer. Okay. I should write this v 1 to r. In fact, it is positive, r plus you can also write. Okay, so now let us come to this non-autonomous system. So now here in the right hand side you have t. Okay, so analogous to what we have seen so far for autonomous system, we have a different kind of theory, okay, related to Lyapunov stability and or asymptotic stability. So suppose this ft comma 0 is 0 and ft comma y is non-zero other than y equal to 0. So basically this tells you that the equilibrium solution y equal to 0 is an isolated equilibrium point. Okay, so this thing tells you that it is isolated. The equilibrium point 0 is isolated. Okay, nothing much. So okay, so this is a definition of class K. So a function phi of r is said to be of class K if this phi at 0 is 0. So it is, first thing is, it is non-negative. Okay, and phi at 0 is 0, and phi of r is an strictly increasing in r. So phi is a strictly increasing function, and which starts with 0 value. Okay, so the domain of phi is 0 comma rho is any real number. So phi at 0 should be 0, and phi of r is strictly increasing. Okay, so that function is called of class K. Now, so Lyapunov function. Okay, so again we have to define this positive definite. So it's, the argument is, the definition is similar to what we have seen. So the first thing is that it should be this, where is it? So vt comma 0 should be 0. Okay, so everything is with respect to y, the second variable. So vt comma 0 should be 0. Okay, and there exists a phi of class K which is bounded, which bounds below the function v. Okay, so the first thing is clear, that it's analogous to what we have seen, that vt comma 0 is equal to 0. The second property tells you that vt comma y should be bounded by a function which does not involve t. Okay, so that's one thing, that this does not involve t. Okay, so this is uniformly bounded by this kind of function which is strictly increasing, and this is non-negative. This phi at 0 is 0, but otherwise it is obviously strictly greater than 0. So if y is non-zero, right, from the definition of class K. So in the earlier case, when we talked about Lyapunov function, that v is a positive definite, then you can actually tell that if v is strictly this positive definite function, then there will exist a function phi which satisfies this property. So when t was not involved. Okay, so in earlier case also you can guarantee such a result, but here we use this as a definition. Okay, so this is kind of similar to what we have seen for the earlier case, like when the system was time invariant or autonomous. Okay, so this is the definition of positive definite, that the first thing is that it should be 0 at y equal to 0, and vty should be bounded by class K function, okay, in this way. Okay, another definition is of discrete function. Okay, so function v will be called discrete if the first thing is the same, that v at t at 0 should be 0. The second condition, so instead of having a lower bound, the v should have an upper bound. Okay, then it's called decreasant. So here we had this lower bound for positive definite. Here we are asking for this upper bound for this decreasant function. Okay, now let's come to the theorem. So if there exists a positive definite function v which satisfies this, the same condition what we saw earlier, that vt comma yt should be less than equal to 0, then the solution is stable. The trivial solution means y equal to 0. Okay, so y equal to 0 is stable. Now if there exists positive definite discrete function, so positive definite means it should have a lower bound, and discrete function means it should have a upper bound. I mean upper bound of by this class K functions and lower bound by class K functions. So basically v of y should be less than equal to psi of norm y and greater than equal to phi of norm y, where phi and psi are class K function. Okay, so if there exists such function which satisfies this property, that is strictly less than 0, okay, then the system is asymptotic stable. Okay, so this is the theorem. So here there is no theorem about instability, we just have these two theorems. Okay, so we'll just see one example based on that. So you consider this system. Now you see this matrix is time dependent. Okay, so if you want to write it in this block form, you can write it as a system in this way: y1 prime t equals y2 t and y2 prime t equals minus 1 plus e minus t y1 t. Yeah, so this is the system. Okay, so now you have to check. So the first thing is clear, right? So you see what is the equilibrium solution. So if I equate y prime equal to 0, then the first equation tells me that y2 t is 0. The second equation tells me that minus 1 plus e minus t y2 t is 0. Now you know that this quantity is always non-zero because exponential is positive function. So this is non-zero. So this would mean that y2 t is 0. So this tells me that y equal to 0 is an equilibrium solution. Okay. Okay. Now let us check the stability of this this y. Okay, y equal to 0. So I mean, let's try to go in a fashion what we used earlier. So you see this is the equation: y1 prime equal to y2, y2 prime equal to minus y1 minus e minus t y1. Okay, so if you forget about this x, so as of now let's forget about this term. Okay, so then if you multiply this by y1 and this by y2, what you get is y1 prime plus y2 prime equals y1 y2 minus y1 y2. So this is 0. So you got that d dt of y1 square, okay, then this is 0 plus y2 square is 0. Okay, so in this case you are getting 0, but the main thing what I want to tell you that this cross product term is cancelling, right? So over here this term will play a role in getting the desired property, right? We want the derivative to be strictly negative, like this kind of thing. Okay, so we'll have to change a so this is my, I mean we should look for v. So Okay, I haven't mentioned earlier, but this is how we look for V. Like when you go through energy functionals, just multiply, try to cancel out. So what I was telling you earlier also, that try to cancel out the cross product terms. So similar kind of thing you can do to get this expression of V. Okay, but over here this is not my V, obviously, because the derivative is becoming 0, identically 0. So this is not what we want, but over here we have this term, extra term. Okay, so instead of doing that, what we can do, so okay, this y1 is cancelling this term, that is fine, this term. Now for the other term, so what you can eventually do, so instead of choosing this multiplier, what you can in fact do is so y1, so you can maybe, so let's, if I do e minus t and then y1, then I'll get y1 y2, and here also I'll get y1 y2, correct. So now just to cancel out this term, okay, so now you use this multiplier. Okay, so then what you get is y1, if I use this multiplier, then I'll get y1 prime times y1 plus e minus t y1 plus y2 prime times y2 equals to 0, right? Because this y1 y2 will cancel out, and this e minus t uh, e minus t y1 y2, and here you will get minus e minus t y1 y2. So this will be 0. Okay, so if I try to write this up, so what I'll get is d dt of, so half y1 square, and then I'll get here what is the extra term, so this will be e minus t y1 y prime. So let me write in this way better. Okay, so this is y1 prime y1 1 plus e minus t plus y2 prime equals to 0, right? Now then what I can do is, just a second, so this is what I want. So just a second, so what I wanted is, so let me see what is my, so what I want is del v by del t, sorry, dv by dt should be negative, right? This is what my goal is. So dv by dt, I know dv by dt is del v by del t plus del v by del x1 or y1 times y1 prime, correct, plus del v by del y2 times y2 prime. So this is, and this I want, this should be negative, this is my goal, correct. Over here what I'm getting is y1 prime times something, y2 prime times y2. Okay, so this should be my kind of, okay, so what is my del v by del t? Okay, let me see that if I take del v by del y1 to be this one, this quantity y1 1 plus e minus t, if I do this, then if I integrate, so what I get is v of y1 comma y2. So this I'll get as 1 plus e minus t y1 square, right? Correct. Okay, so then what you do, then I think then it's clear. Okay, let it be. So now you define v of t comma y1 comma y2. Okay, so what you do, you just define, so from here if you do del, so you know del v by del y2 is y2, right? So this will gives v will be y2 square. So this is some constant is involved. Now this constant is a function of t and y1. Okay, so this is a function of, maybe I should try it, plus c of t comma y1, sorry y2. Okay, and if you integrate this, you will get y1 square, okay, y2 square. So let's define this v. So now define v as 1 plus e minus t y1 square plus y2 square. Okay, if I do this, I think this should work. So let us see the del v by del t. If I do, what I get, so I'll get e minus t y1 square, so minus e minus t y1 square, del v by del y1. If I do, I'll get 2 1 plus e minus t y1, and del v by del y2. If I do, I'll get 2 y2. Okay, so dv by dt, if I do, it is nothing but del v by del t plus del v by del y1 into y1 prime, del v by del y2 into y2 prime. So del v by del t is minus e minus t y1 square, and you know that this quantity is 0, right? From the above earlier calculation, you see del v by del y1 and del v by del y2, y1 prime y2 prime, so this is 0. So you got this quantity. Now clearly this is strictly less than, okay, so this is not strictly less than 0. Okay, so let us verify all the properties. Okay, so this I can say this is strictly less than equal to 0, because if I take y1 to be 0 and y2 to be anything, then I know that this could be 0. I mean, this is 0. Okay, so I cannot say it is strictly less than 0. Okay, now let us check the main property of v. So we wanted v to be positive definite, right? So I'll conclude. So using this, I want to conclude that y equal to 0 is a stable solution. Okay, so this is what I want to conclude. So for this conclusion, you just recall that what you needed. You want the positive v to be a positive definite function. So this you have already verified that this is true. So you only need to check that this v what I have obtained, whether it is positive definite or not. Okay. Okay, so you can clearly check here. The first thing is that for positive definite you need that v t comma 0 comma 0. If I put, I am getting it 0. So the first condition is checked, right? The second condition you need is that it should be bounded below by some k class function, right? So if you see v t comma y1 y2, if I do, now this quantity, so e raised to the power minus t, you know, it is always greater than 0, right? It is a positive function. So I can say v t comma y1 y2 is greater than equal to, okay, y1 square plus y2 square. This is nothing but phi of norm of phi, right? Now this is a class k function, obviously, correct? So all these conditions are verified. This is a strictly increasing function, and at 0 it is a 0. Okay, so maybe I should write it in this fashion to be, this is norm y square and this is my function phi. So phi of x equal to x square, you know that this is strictly increasing for positive functions for x. So strictly increasing for x greater than equal to 0, and phi at 0 is 0. Okay, so this is a class k function. Okay, so using this Lyapunov function, this one, I can conclude that y equal to 0 is a stable equilibrium solution. So I cannot guarantee anything about whether it is asymptotic stable or not. For that, maybe some other Lyapunov functional may work or may not. I don't know that about that. But what I can say that y equal to 0 is a stable equilibrium point. It may or may not be asymptotic stable. Okay. Okay, so that's it for today. Do you have any
I-
question?
uh,
Yeah,
we have written phi of x equal to x square. No? That
correct.
x square is because we got the norm y square.
Yeah,
Okay. So here x square means it is a norm. It is not a simple scalar, right? Phi of x
yeah,
need
it
not.
is scalar function, right? If you see, when I say phi of norm of y is a real number, right? A positive real number.
Yes.
So that's why I've written phi of x equal to x square.
Okay.
So it is defined on real line. It is not a vector
Here,
valued.
here actually we are deriving the class k function, right?
Correct, correct. So you see the definition of class k function there. You know that this phi is a real value. I mean, defined on a real line and taking the value in positive real line. Right. So this phi is said to be class k if phi is from 0 row to r plus phi at 0 is 0 and then phi is strictly increasing.
Now here the sequence to find the stability of non-autonomous system is first we have to derive the Lyapunov function
No,
from
actually,
our
no,
state
this
equation.
argument what I gave, you basically have to guess what the Lyapunov function is, right?
Yeah, okay.
Now, generally, we do it in this kind of fashion. Like when you have a system, you try to cancel the cross product terms. I mean, this argument what I gave is true even when it is autonomous system. Okay, so when you have system, you basically try to do it in this fashion. So although here I have shown you a variational approach, what what has been mentioned in the lectures, but in general when you deal with problems, the first approach generally people use is this kind of thing. Okay, when the system is smaller, let's say 2 cross 2, then you try to deal it in this fashion. So here I just demonstrated that argument can be generalized in this fashion. So maybe it's kind of guess that how you want to derive this Lyapunov function. So this is how you try to guess the function. That's it.
Okay.
So this is not specific to non-autonomous. I mean, this is a general argument what people generally use. Is there any other question or comment? Okay, if not, then let's stop here. See you next week then. Okay,
Okay, thank you. Good night.
bye. Good night.